All right, we're in section 4.6, and we're talking about another method of solving non-homogeneous linear differential equations. And the method here is called variation of parameters. Now, this technique can be used to solve the same types of DEs that we solved back in the previous two sections where we were looking at undetermined coefficients. But actually, it's a little bit more powerful than that because the technique that we're talking about here does not require your DE to have constant coefficients. It still needs to be linear. We're still talking about linear differential equations and non-homogeneous in that case as well, but we don't require these to be constants. These can just be, any function of x as long as, this is a linear DE. Now, that makes it more powerful in theory, but as you're going to see, we're still going to be looking at DEs with constant coefficients here, and the reason for that is because this technique requires you to know the complementary solution for your DE. And so far, we've only really talked about how to come up with complementary solutions for those higher order differential equations when those coefficients are constants. We in the next section, when we look at Cauchy-Euler equations, we'll talk about how to come up with those complementary solutions for linear DEs where these are not constants, but they have a very, very specific form. So anyways, that's a lot of kind of preliminary stuff. Let's get into it. So what we're doing here is, once again, we're going to be focusing on non-homogeneous DEs that are linear, and we're actually going to be focusing exclusively on second order equations. Now, I'm going to say this now, and I'll probably say it again at the end. This technique works for higher order DEs than just second order. Okay, but it gets very, very complicated the higher the order of the equation, and our focus really just needs to be on the second order case here. So first of all, if you're given a second order linear non-homogeneous DE like this one, our first goal is to make sure that the leading coefficient, the coefficient on your y double prime term, is a 1. So if necessary, we would divide everything by this a2 of x right here, putting our DE into this form. And I'm just going to be working with this form from here forward. Y double prime plus some function of x, p of x, y prime, plus another function, q of x, y, equals f of x, some other function of x. Now, like I had already sort of mentioned, this technique requires you to already know what the complementary solution for this is. And again, if these are constants, these coefficients up here, we know how to come up with this. If they are not, then the complementary solution either has to be given to us ahead of time, or we need some technique for finding this. But suppose we have managed to come up with a complementary solution for this DE. Now the next goal naturally would be to find a particular solution so that we could put them together and create a general solution. But really the only thing that we have to work with is that complementary solution that we would have found ahead of time. So the goal here is to try and see if we can use our complementary solution in some specific way to come up with a particular solution. And what we're going to be doing here is very similar to what we did in section 4.2, where we talked about reduction of order. If you recall, in the reduction of order case, what we were trying to do was come up with a fundamental set of solutions for a second order differential equation, and we said that if we're going to have a fundamental set of solutions, we need our two solutions that we come up with, y1 and y2, for example, to be linearly independent. They need to belong to a linearly independent set. And then we said if they were linearly dependent, then one function would be a constant multiple of the other. So to guarantee that we don't have linear dependence, we change that constant to a function of x, right? And then we kind of came up with a formula from there. So we're going to sort of mimic that. The complementary solution to this DE involves these constant parameters, C1 and C2. And what we're going to do is say what would happen if we, let's suppose that we're able to find a particular solution by changing these constants, C1 and C2, into functions of x. specifically some non-constant functions of x. If we are able to do that, then we know that this thing couldn't be a solution to the associated homogeneous equation, so because it's not coming from our complementary solution. But if we select u1 and u2 carefully, if we find specific functions u1 and u2, we might be able to create a particular solution. So that's what we're doing. We're going to assume that we've managed to find a particular solution that looks like our complementary solution, but we've replaced our constant parameters with these variable parameters. And this is where the term variation of parameters comes from. That's where this technique comes from. Okay, so if this is a particular solution, then I should be able to take this thing and plug it into my DE up here and get f of x. It should satisfy that DE. So first things first, I would need to find yp prime and yp double prime, which we have here. Notice I need to be applying the product rule a couple of times. So these derivatives tend to get very, very messy. Okay. Now what follows, you'll notice this is directly out of your book. I copied and pasted this whole thing because I don't see a point in retyping all of the exact same stuff. But I am going to sort of talk you through it. What follows here is a lot of algebra that we're skipping. So if you look, we have to go back up to our original DE, our yp double prime, this term, we're going to substitute this gigantic expression with 8 terms into just this one guy right here. And then p of x times y prime. We're plugging in yp prime, which has 4 terms, so that p of x has to distribute over all 4 of those terms. And then y, which is going to be yp when we plug it in, is this thing, right? So it gets very, very messy. And you'll see right here where we substitute these things into your DE, the expression on the left-hand side of your DE. The next step has already done a whole lot of regrouping of those terms. Okay, so because the algebra is so involved, I'm not going to go through and show you where every single one of these comes from, but I am going to point out the important stuff. So here's what has happened. After plugging everything in, you're going to get a whole lot of terms floating around. And if you were to group up all of the terms that have a u1 in them, and all of the terms that have a u2 in them, and then factor the u1 and the u2 out, what remains in brackets here is y1 double prime plus py1 prime plus qy1, and the same thing but with y2s instead of y1s. Now why is that important? Well, y1 and y2 were the fundamental set of solutions for our associated homogeneous equation that we used to come up with this complementary solution. There's where y1 and y2 come from. What that means is that both of these, when plugged into this DE on the left, or the expression on the left-hand side, should give us a 0. That's what the associated homogeneous equation does, right? So both of these go to 0, which is super convenient because a big chunk of all this mess here is going to just disappear. All right, but then we still have all of these terms floating around to deal with. Now, you're going to notice that in a couple of these cases, for example, these two terms right here, y1 u1 double prime plus u1 prime y1 prime. This looks like the result of applying the product rule to y1 u1 prime. So these two terms can be consolidated down to this. Okay. Similarly, these two terms are the result of the product rule being applied to y2 u2 prime. So these two terms can be consolidated down to ddx of y2 u2 prime. Okay, and then the other terms that were left over, which we haven't changed from this step to this step, are still there. 2 of the terms had a p or p of x that showed up in there, and that p has been factored out. So that's how we get from here to here, and then going from here to this next step, we take this derivative and just represent it as a derivative of the sum of these two terms right here. Okay, so that's taken a very, very messy expression and done a great deal to simplify it. Still very messy, right? And at the end of all this, it should equal f of x because, again, we're assuming that we have a particular solution to that DE up there. Now, if you look carefully, you'll notice we have a couple of things in square brackets, and the expression in both square brackets is the same thing. y1 u1 prime plus y2 u2 prime, same thing in here, okay? So what we can't forget what the goal of all of this is. The whole point of this tedious exercise is to try and determine what U1 and U2 are, such that they give us a particular solution when we put them into this. So we're trying to solve for U1 and U2. Now notice U1 and U2 by themselves have disappeared all the way up here. They zeroed out from these two steps. But I'm seeing U1 prime and U2 prime floating around. And if I can solve for U1 prime and U2 prime, then I can get U1 and U2 from those by integrating. So the goal is to solve for those two unknowns, U1 prime and U2 prime. I already know that if I have a system of two linear equations in two unknowns, we have methods for solving those. So I would like to generate a system of equations using this thing as a guide. Now, notice it would simplify this expression a great deal if that y1 u1 prime plus y2 u2 prime, the thing that's showing up in both square brackets, was equal to 0. Because if that expression was equal to 0, then I would get to cancel both of those terms, and all that would be left is this little guy right here. So we are just going to assume that that's the case. Assume that this expression in either of these square brackets is equal to 0. If that's the case, then what's left is y1 prime u1 prime plus y2 prime u2 prime equals f of x, giving us a second equation. So we've assumed this equation, and as a result, it gives us this one from the work we did previously. There is our system of equations. Now, it may not look like a system of linear equations that you're used to, because the y1 and the y2, the y1 prime and the u2 prime, are not constants, not necessarily. However, they are known to us, because remember, those came from that complementary solution, which we are assuming we already knew. So the only unknowns are the u1 prime and the u2 prime here, and we get to treat the y1 and y2, y1 prime, y2 prime as constants as we would when solving a regular old system of linear equations. Nothing about the techniques for solving this is going to change. So we want to solve the system of two equations and two unknowns, and what we're going to use to solve it is Cramer's rule. Now, I'm not going to assume that you have seen Cramer's rule before. However, Cramer's rule can be taught as early as intermediate algebra. I have actually taught Cramer's rule in an intermediate algebra course, our Math 120. And I have only done it once. It ended up confusing students a lot, and so I haven't taught it since then in that class. It's also frequently covered in pre-calculus. It's often covered again in linear algebra, because in linear algebra you can actually prove it. But it's a technique for solving systems of equations. So I'm going to review that here in case you haven't seen it, so you can see where it applies and what we're doing. Let's start by looking at a 2x2 system, the kind of system of equations that we have. Let's suppose that we have this system of two equations and two unknowns, x and y. The coefficients are a1 and b1 here, a2 and b2 here, and the constants are c1 and c2. This system can be solved using determinants. Three determinants in particular. So D, I'm going to call this D, is the determinant which just contains the coefficients in the order that you see them here. A1, B1, A2, B2. You see them showing up right there. That determinant is going to play a role in our solution. And then we define these two other determinants, D1 and D2. And these two determinants come from this first one by replacing one of the columns in this with the constants C1 and C2. So if I'm D1, I'm replacing the first column. That's what the 1 is for, replacing the first column with C1 and C2. D2 replaces the second column with C1 and C2. Okay? If I've evaluated all three of these determinants, then the solution to this system is going to have an x and a y value. The x is equal to D1 divided by D. Y is equal to D2 divided by D. Okay? And we can prove that. But we're not going to do that here. That's better left to a linear algebra course. We're just going to take this for granted. Now, let's look at a 3x3 system. Does Cramer's rule apply to that? Yes. And it follows a similar pattern, but being 3x3 is just going to look slightly different. So again, we have a system of three equations in three variables. x, y, and z. The solution to this is also going to be found using determinants, and this time we need 4 determinants. We still calculate one called d, which contains only the coefficients on the left-hand side of each of these equations in the order they appear in: a1, b1, c1, a2, b2, c2, a3, b3, c3. You can see them all showing up here. Then we define d1, d2, and d3, similar to how we did in the 2x2 case, where we replace whichever column is indicated by that subscript, first, second, or third column, by the constants on the right-hand side. So you can see the d1, d2, d3 showing up in my first column here, second column here, third column here, and the other columns are just going to match what we see in D. Then x, y, and z are found by dividing one of these determinants by this d right here. Okay, and you can generalize that to any n by n system of equations. It doesn't have to be 2x2 or 3x3. We're only going to be looking at 2x2s in this case, so we don't need the more general case. Okay, so looking back at what we had done here, if we want to apply Cramer's rule to this, the coefficients now, remember they're not constants anymore, the coefficients are functions of x, y1 and y2, y1 prime, y2 prime. My coefficient matrix, my coefficient determinant, is going to just contain those y's and y primes, okay? But I have that down here. We're going to call that w instead of d, like we did in Cramer's rule. And the reason for that is because it's actually the same thing as the Wronskian. It's the Wronskian of y1 and y2. That's what that determinant would be equal to. Now, still using Cramer's rule, I'm supposed to be replacing one of these columns with the constants in my system of equations. Only we're not looking at constants anymore. One of these is a constant, 0, but the other one is an f of x. So we're replacing a column in that determinant w with a 0 and an f of x. In the case of W1, I replace the first column. In the case of W2, I replace that second column. Now I've gone ahead and evaluated these determinants because both of them are 2x2s, and those are easy to solve, or easy to calculate, especially when one of your entries is 0, because, again, what is W1 going to equal? 0 times y2 prime, which is just 0, minus y2 times f of x. So it comes out to negative y2 f of x. Similarly, W2 is equal to y1 f of x. Okay, Cramer's rule says that when solving for those unknowns, u1 prime and u2 prime in this case, we would take w1 and divide it by w. That gives me u1 prime. w2 divided by w is u2 prime. But having evaluated w1 and w2 a little bit more explicitly, we can also write these solutions this way. Okay, what this does for us is it tells us what u1 prime and u2 prime look like. Then we can find u1 and u2 by integrating those. Then we take the results, put them into this thing, and now we have a particular solution. Okay? Now, that took a fairly decent chunk of time to derive, and in a lot of the techniques that we've talked about for solving DEs, we have said, make sure that you go through the work of deriving this technique instead of memorizing a formula, right? This is a case where we don't want to do that. And the reason being is because of all this mess. You don't want to deal with all that every single time you're solving a DE using variation of parameters. In this case, we really do just want to remember a couple of formulas. And fortunately, the formulas are not terribly complicated, right? This is essentially all you're memorizing. You do have to remember that W is the Wronskian of y1 and y2, but we've dealt with Wronskians before, so it's not really memorizing something brand new when you're thinking about that W. As long as you can remember these formulas, you start, well, you don't start here, you have to find your complementary solution, but you're basically not going through all of that derivation, you're just going with what we have here, okay? So I'm going to do my examples in the next video. So let's go ahead and end this one here.